Hello everybody, and today we'll be talking about the Wittig reaction. Here I have my assistant Nala to help us out with the process. The Wittig reaction was discovered by a German chemist named Georg Wittig. He discovered a class of organic phosphorus compounds called ylids that became reagents in the famous Wittig reaction. The Wittig reaction is a chemical reaction of a carbonyl compound, either aldehydes or ketones, with a triphenylphosphonium ylid, known as a Wittig reagent, and an alkene and triphenylphosphine oxide is produced. Georg Wittig discovered this reaction in 1954 and was awarded the Nobel Prize in Chemistry in 1979. To begin, I will show the mechanism of the Wittig reaction. In this example, we'll be starting with an aldehyde and a phosphonium ylid. A phosphonium ylid is a Wittig reagent and is a molecule that has adjacent atoms with opposite formal charges. It can also have an important resonance form where a double bond is formed between the phosphorus and carbon atoms. The phosphorus atom is positively charged and has 3 phenyl groups attached to it and a bond to a carbanion. To start the mechanism, the electrons on the negatively charged carbon will attack the electron deficient carbon. This carbon is electron deficient because of the resonance structure the aldehyde can form. So this is what we get. Now we have an intermediate form. The electrons on the oxygen can attack the positively charged phosphorus, creating a box structure. Next, the bond here can attack the bond between the electronegative oxygen and phosphorus, and this forms a double bond in phosphine oxide. Phosphorus will have too many electrons, so it will give up the electrons in the bond between itself and carbon and will give itself to form the double bond in the alkene structure. Lastly, this brings us to our product. So our products are an alkene and phosphine oxide. The geometry of the resulting alkene depends on the reactivity of the ylid. Ylids can form either Z or E alkenes, where non-stabilized ylids lead to Z alkenes and stabilized ylids lead to E alkenes. Nala, do you agree? Perfect. Next, I'm going to backtrack a little bit and discuss how a phosphonium ylid is made. To start, triphenylphosphine will undergo an SN2 mechanism with an alkyl halide. Triphenylphosphine will only attach to 0 degree, 1 degree, or 2 degree alkyl halides. It will not occur with tertiary alkyl halides because SN2 reactions do not work with tertiary alkyl halides because they are too bulky. First, the electrons on the phosphorus will attack the carbon of the alkyl halide, and the bond between the carbon and the leaving group will break. Now we have this intermediate form, and the phosphorus is positive because it lost electrons. Lastly, deprotonation occurs, and the hydride here can attack the hydrogen over here. And the 2 electrons in the bond move on to carbon, giving it a negative formal charge. And lastly, that is how our product is made, a phosphonium ylid. Biologically active compounds can be synthesized from the Wittig reaction, including things like vitamin A, vitamin D, steroids, prostaglandins, and much more. Particularly, it can be used in the synthesis of beta-carotene. Beta-carotene is a red-orange pigment found in many fresh fruits and vegetables, and is converted into vitamin A, which is an essential vitamin. Some important features about beta carotene is that it is an antioxidant, it can help slow cognitive decline, as well as it can keep people's lungs healthy as they age. That brings us to the end of our discussion. I hope you enjoyed watching. Thank you very much.